Chemical reactions. Welcome to our session on chemical reactions. In Thermodynamics 2, we go beyond just energy balances and cycles. We start to look at how matter itself transforms. Chemical reactions are everywhere, from combustion engines to industrial reactors, even inside our own bodies. Understanding them is crucial because these reactions release or absorb energy, and they change the composition of substances. Today, we'll break down the basic principles that help us analyze chemical reactions from a thermodynamic perspective, making sense of enthalpy, entropy, and chemical equilibrium in practical systems. Let's get started and see how chemistry and thermodynamics work together to power the world around us. 1. Learning outcome. Before we dive into the technical details, let's get clear on what you'll take away from this chapter. First, you'll get an overview of fuels and combustion, understanding what we burn and why. Next, we'll focus on the core principle of mass conservation in chemical reactions, because every atom must be accounted for. You'll also learn key combustion parameters like air-fuel ratio and theoretical air, which are crucial for efficiency and control. We'll calculate enthalpy of reaction and heating values to see how much energy is released or absorbed. Energy balance will show you how to track energy flows, while adiabatic flame temperature gives insight into the peak temperatures achievable. Entropy change and second law analysis will help you assess the direction and efficiency of reactions. By the end of this chapter, you'll be able to apply both the first and second laws of thermodynamics to real-world chemical reactions. 2. Fuels and combustion. Let's begin with the foundation, fuels. Simply put, fuels are materials we burn to release energy. Most of what we deal with are hydrocarbon fuels, made up of hydrogen and carbon, which we write as CnHm. These come in different forms: solid fuels like coal, liquid fuels such as gasoline and diesel, and gaseous fuels like natural gas and LPG. Each has unique characteristics, but follows the same basic principle: burn it, release energy. Next, we need to understand air composition. Combustion happens with oxygen, but in air, oxygen is only 21%. The rest, about 79%, is nitrogen, which doesn't react, but affects the combustion process. That's why, in calculations, we often use the ratio of O2 to N2 as 1 to 3.76. Finally, the combustion reaction itself is straightforward. Fuel reacts with oxygen to produce CO2, H2O, and N2. If the combustion isn't complete, you may also get CO, which is less efficient and more harmful. This simple understanding helps us analyze complex systems like engines, boilers, and power plants much more easily. 3. Theoretical versus actual combustion. Now let's talk about the difference between theoretical and actual combustion. In an ideal world with complete combustion, all carbon turns into CO2, hydrogen into H2O, and sulfur into SO2. This is the cleanest and most efficient outcome. But in reality, incomplete combustion happens, especially if we don't supply enough air. This leads to carbon monoxide, CO, or even soot, which wastes energy and creates pollution. That's where the concept of theoretical air comes in. It's the exact amount of oxygen needed for complete combustion. However, in real systems, we often use excess air, more than 100% of theoretical air, to ensure full combustion and reduce harmful byproducts. For instance, 50% excess air means we supply 150% of the required air. On the other hand, when there's a deficiency of air, below 100%, we risk incomplete combustion, which leads to lower efficiency and more pollutants. Balancing this air-fuel mixture is crucial for optimizing performance in any combustion system. 4. Air-fuel ratio, or AFR. Next, let's break down the air-fuel ratio, or AFR. This is simply the ratio of the mass of air to the mass of fuel during combustion. It tells us how much air we need to completely burn a certain amount of fuel. There's also the fuel-air ratio, which is just the opposite, fuel over air. To make this clearer, let's look at a simple example. When we burn octane, which is H18 with air, the balanced equation shows us how many moles of oxygen and nitrogen are involved. From this equation, we calculate the air-fuel ratio, and for octane, it comes out to 24.2 kilograms of air for every kilogram of fuel. This number is crucial. It helps us design engines and combustion systems for efficiency, power, and lower emissions. 5. Enthalpy of formation and enthalpy of combustion. Now, let's talk about energy changes during reactions, starting with enthalpy of formation. This tells us how much energy is released or absorbed when 1 kilomole of a compound forms from its basic elements. For example, when CO2 forms, it releases negative 393,520 kilojoules per kilomole. Next is enthalpy of combustion. This is the heat released when 1 kilomole of fuel burns completely. Take methane, CH4, for instance. It releases negative 890,330 kilojoules per kilomole when burned to form CO2 and liquid water. Finally, we have higher heating value, HHV, and lower heating value, LHV. HHV assumes water vapor condenses back to liquid, capturing more energy. LHV assumes water stays as vapor, so less energy is counted. The difference between them is simply the energy from condensing the water formed during combustion. This distinction is essential when comparing fuel efficiencies across different systems. 6. First law analysis of reacting systems. Let's now apply the first law of thermodynamics to reacting systems, specifically combustion. The energy balance equation states that the heat and work going into the system equals the difference in enthalpy between products and reactants. This accounts for both the enthalpy of formation and the sensible enthalpy due to temperature changes. To see this in action, we look at a steady-state combustion example burning propane, C3H8, with 150% excess air. This means the air-fuel ratio is 25.53 kilograms of air per kilogram of fuel. From the calculation, the heat released from the combustion chamber is 363,880 kilojoules per kilomole of propane. This first law approach helps us quantify energy flows in practical combustion systems, like furnaces or engines, ensuring efficiency and energy conservation. 7. Adiabatic flame temperature. Let's talk about one of the most important combustion characteristics, the adiabatic flame temperature. This is the highest temperature that combustion gases can reach when no heat is lost to the surroundings. It's an ideal scenario, but very useful for theoretical analysis. Several factors affect this temperature. First, the type of fuel. Different fuels release different amounts of energy. Second, oxygen concentration. Using pure oxygen instead of air raises the flame temperature because you're burning with more oxygen and less inert nitrogen. Third, the amount of excess air. Adding more air actually lowers the flame temperature because it absorbs heat without reacting. For example, burning octane, C8H18, with just enough air or 100% theoretical air gives a flame temperature of 2395 K. But if you increase to 400% theoretical air, the temperature drops sharply to 962 K. This shows why controlling air input is crucial in designing combustion systems. 8. Entropy change in reacting systems. Now we shift focus to entropy, a key measure of disorder and energy dispersion in reacting systems. For combustion processes, we use the entropy balance, which says that the entropy generated equals the entropy of the products minus that of the reactants. In adiabatic processes, where there's no heat loss, entropy generation is always greater than or equal to 0, reflecting the second law of thermodynamics. To visualize this, let's look at an example. When methane burns with excess air, the entropy generation is 966 kilojoules per kilomole per Kelvin. This means a significant amount of energy is irreversibly spread out. Additionally, exergy destruction, which measures lost work potential, reaches 288 megajoules per kilomole of methane. These numbers show how combustion, while releasing energy, always comes with some unavoidable losses in quality and usability of energy. 9. Second law analysis of reacting systems. Let's look at the second law analysis, which helps us understand the quality of energy, not just the quantity. In real combustion systems, some energy potential is always lost due to irreversibilities. This is called exergy destruction. We calculate it by multiplying the ambient temperature with the entropy generated. The reversible work is the maximum useful work we could get if there were no losses. It's found by subtracting both the enthalpy difference and the entropy-related losses from the reactants to products. For example, when burning carbon with oxygen, the reversible work comes out to 169,680 BTUs per pound mole. This tells us the absolute best-case scenario for energy conversion, helping engineers see how far real systems deviate from ideal performance. 10. Final summary. Let's wrap up everything we've covered. Combustion isn't just about burning fuel. It's a complete process involving mass conservation, enthalpy balance, and entropy considerations. Whether combustion is complete or incomplete significantly affects both efficiency and emissions. We explored how enthalpy of formation and combustion are central to understanding energy flow. Air-fuel ratio and the use of excess air play big roles in flame temperature and efficiency. We also saw that adiabatic flame temperature is a crucial parameter when designing engines or burners. Finally, by examining entropy generation and exergy destruction, we can clearly see where energy is wasted and how efficiency drops. Mastering these concepts helps you analyze and optimize any combustion system you encounter.